So we've seen this concept of generator methods. Let's go apply it to everything we have going on here. And I'll even show you another keyword we haven't had a chance to talk about yet. So let's start at the bottom. Here's a method that is a traditional method. It puts all the stuff into the list. And then once that computation is done, everything is computed. It returns that whole list. And then we just have another list above that we add even more to and keep extending as we hit more and more files. We can do better. So instead of doing matches here, let's get rid of this. And instead of doing append M, we will say yield M. And we won't have to return the matches. Maybe I'll leave that commented out for you. Like so. So no more list, we're just doing yield. Now this would already work. What we're doing is calling up here, search file, and here we get our generator, but we can take any collection, generators are iterable collections, and extend this list. But we can actually do better still. So this is a generator method. This is a regular one, but we can also apply the exact same idea here and the same idea here. Now this gets a little tricky because I have to say for M in matches, yield M. Now that's not the most fun thing to write. It would work, but I'll show you something better. Same thing down here. For all the matches there, we want to do that, and then we no longer have our return. So here's a generator method, and it's going to come through, and each time that we sort of pull something out of this collection, it's going to go until it hits one of these, which is a generator, and it's going to hand one back. So if we only wanted the first 4 matches, we could compute that extremely quickly. However, this line 65, 66, this is not the coolest thing. It turns out that Python 3.3 added basically a keyword that will do the same thing, like take a whole set and sort of hand them back one at a time. And so we can simplify this and just say yield from matches. And if we really wanted to simplify this, we could actually come down here and just write it as one line. We could just say yield from that. Never even store matches here. Similarly, yield from that. So down below we have search files. That individual searching of a single file is a generator, and we only ever have a single line in memory at a time. Now up here, as we work through all the files in a directory, or even recurse into a tree of directories and their files, we are only pulling back one item from either here or here at a given time. And that means we only have one line in memory at a time, really one search result. And then we can go up here and we're printing out. Now let me just show you that this is still working. Let's bring this back in and let me search the simple files again, just to show that we're actually still searching just like before. So let's search the small set of books for Holmes. There you go. We can see 468 matches, and we're searching Ulysses. We're searching The Adventures of Sherlock Holmes. Perfect. It works exactly the same, but from a performance perspective, it's not the same. Let's run it again. And this time, we're going to search the large set of files. And again, we're going to search for how many question marks are there. There was something like 2.78 million question marks. And remember, we had to use like almost 400 megs of memory to answer that question. Remember, 400 megabytes. What's it going to do this time? Can we do better? Oh, here, hold on. Let me stop this really quick. Remember, we didn't do the output. It was too much when we really ended up doing that. We just did our little count. So let's rerun it this way. Okay, here we go again. It's going 3.8 megs. Remember, should it jump up to 300 megs, a gigabyte? What is going on? This is so absolutely amazing. Look at this, you guys. We are processing gigabytes and gigabytes of code with almost identical algorithms. And yet the memory usage is the same as if we're processing like a single line in memory, because that's all we're ever holding is a single line in memory. Granted, we do have the file stream open to some huge file at some point, but we're seeking over it. We're like streaming across it. Let's just let it run and see where it goes. It's done. Look at that. Look at the memory usage. Look at the CPU. Look at the performance. It is so much better than it was before. In fact, I kept the previous one around. Let's have a look at it. It's not really fair to put them side by side because the scale of the graph is not the same, but I think we'll get a sense anyway. So on the left is the old bad sort of standard procedural code style. And look at the memory. It goes from 3 megs when it was starting out to 394 megabytes. Ours went from a whopping 3 megs to 4 megs. And that was it. If you look at the size of the CPU graph, or sort of the length of any of these graphs, you'll see they're basically identical in computational time. It looks actually lower on CPU usage. Presumably it's doing less garbage collection, less allocation, doubling of lists and copying them and things like this. And all we've done to change the algorithm is use the yield and yield from keyword instead of making lists, appending and extending them. The code we wrote actually got a couple of lines shorter. So this is the power of generator methods. And anytime you're processing like a pipeline of lots of data, you saw that you can chain them together to create these pipelines basically effortlessly. We'll see that there's even a simpler way to create this type of structure, something called a generator expression, right? But we'll save that for the next app.